All right. Today's topic, one of my personal favorites, magnets. Woo! We'll subtitle it, How the Blank Did They Work? So, full disclosure, we're not going to get too far into how exactly they work because, they just work. All right? We'll get a little bit into how they work, but I mean, it's kind of turtles all the way down, if you know what I'm saying. All right. So anyway, magnets. First, let's talk about what they do. All right. So um, magnets, um, you know, first of all, well, they create magnetic fields around them. Okay. Kind of like how I don't want you to get these two things confused, but kind of like how charge creates an electric field around it. Okay, magnets create a magnetic field around themselves that emanates out into space. All right. Cool. Okay, so we just went and we grabbed ourselves a magnet off the web, in case you're unfamiliar with what a magnet looks like. Um, so some things that we can talk about. So the first thing is that um, people noticed early on that iron displays magnetic properties. Iron or can display magnetic properties. All right. And so something like the that says properties. This picture here is an iron magnet. It's an iron permanent magnet. Okay. So what that means is I can bring other um, iron magnets nearby, and I'll find that this thing attracts or repels them depending on which end of the magnet I push towards here. Okay, so that's the first thing. Iron displays magnetic properties. So any permanent magnet, such as the image above, is called, and this has historical reasons, is called a ferromagnet. It should not be an at sign. It should just be an ah. Okay, a ferromagnet. So permanent magnets are called ferromagnets. They don't necessarily, however, need to be made of iron. Okay, iron can be permanently magnetized. Okay, but nowadays you're finding a lot more ferromagnets are made of rare earth elements. So rare earth magnets, and this is because their magnetic properties are actually much larger than iron's magnetic properties. Okay, in other words, you can make a much stronger magnet for a given amount of space with rare earth magnets than you can with a ferromagnet. And an example of some rare earth magnets that you may have seen were these little round toys. I've heard that because of issues with them being swallowed and how strong they can cause a lot of damage if you happen to swallow these. They can essentially stick together parts of your intestines and cause major issues. I think they've been banned, although I'm not exactly sure. Okay, so that's what those look like if you've ever experienced them. And then you might, if you're into speakers, find rare earth magnets in the magnets on speakers, or often in computer hard drives is where you would find these rare earth magnets. But kind of everyday experience would be more with these ferromagnets. So lots of like fridge magnets and that sort of thing are ferromagnetic. So what do magnets stick to? Well, magnets stick to, we often want to say metal, all right? But it's not necessarily all metal, okay? So magnets, I'm just saying, we're talking ferromagnets still. Ferromagnets will stick to other magnets, which might seem strange because ferromagnets will say stick to your fridge, right? And yet your fridge is not magnetic, right? You can't take a fork and stick it on your fridge, but you can take a fork and stick it on your, assuming it's a steel fork, stick it on your magnet. So something's going on here. So ferromagnets will stick to other magnets. And this brings up another type of magnetism called paramagnetism. And these are non-permanent magnets, like your fridge, okay, that only become magnetized when another magnet is brought near them. Non-permanent magnets that become magnetized in the presence of a permanent magnet, we'll say. Okay, permanent magnet. Okay, so a good example, just to repeat, is your fridge. Okay, the metal on your fridge. Now, the one thing to note here is sometimes fridges nowadays are made of non-magnetic materials like aluminum. So aluminum is not either type of magnetic, right? So if you have an aluminum fridge, sometimes people have aluminum fridges that kind of look like stainless steel, like my fridge is like that. You can't stick magnets to those; it just doesn't work. Okay, so aluminum is not magnetic in any way. So you can't permanently magnetize it, and you cannot temporarily magnetize it like you can with paramagnetism. But your fridge, as long as it's steel, as long as it has some kind of iron in it or other magnetic materials like nickel, for instance, you can stick permanent magnets to it then, right? So some steel is paramagnetic. And in fact, there's a differentiation. We call it hard iron versus soft iron. Okay? And just to note, when I'm saying steel, really, steel is mostly iron. But it has some carbon impregnated into it and probably some other trace elements, okay? So steel, being that it's mostly iron, will display either paramagnetism or ferromagnetism. So hard iron can be permanently magnetized, and then soft iron is paramagnetic. So if your fridge can stick a magnet to it, but is not permanently magnetic, it's a soft iron fridge. It's got steel in it with soft iron. Okay. What this actually means in terms of the chemical makeup, I'm not exactly sure, and I don't want to send anyone down the wrong path, but I do know that the ions of iron, or the oxidation states, if you want, can either be 2+, 3+. So its electron configuration can be one of two ways. Now I'm not sure if this is the reason, but I suspect that it is, because we're about to talk about what the source of magnetism is. Okay, so we're going to have to do a little recall. We're going to have to look at the Bohr model quickly of the atom. So if we look at iron, and we'll use iron specifically since that's what we've been talking about, iron's number 26 on the periodic table, so that means it's got 26 protons. And let me see here, 56 roughly, so about somewhere around 30 neutrons, not that they really matter. And then it's got shells filled with electrons, 26 electrons, okay? Now it's a transition metal, so we can't really draw the kind of 288 scenario. If you're further on in physics, we're talking sp, d, and f orbitals, okay? But what actually is the root cause of magnetic behavior is a property of electrons themselves. So electrons have more properties to them than simply mass and charge, okay? They also have this concept called spin. So if I imagine I have an electron, right? It's got its elementary charge on it. Okay. And has some other essentially numbers that describe what its energy levels are like, essentially where it is in this, ring system of electrons, this hierarchy of electrons that orbit around this nucleus. Okay, and one property that it has is called spin. Now, what is spin really? It's a tough one. It's a property of electrons, and I think just for clarity of helping us think about them, we would think of it like a spinning basketball, either spinning one way or the other. Okay, in reality, what's it like? Well, no one's ever seen an electron, so who exactly knows? But the point is that spin contributes to whether or not an element will be magnetic, paramagnetic, or permanently able to be magnetized. Okay, and it's got to do with how many electrons there are and what orientations their spins happen to be in. Okay, now we're not going to go really any farther into it than that, because you need to kind of do some quantum physics and it all becomes a numbers game eventually. But that's the general kind of idea behind this. So in other words, magnetism, like charge, are caused by fundamental particles inside the atom. Okay? And that maybe shouldn't come as too much of a surprise, because I almost guarantee you've heard of the term electromagnetism before. Okay? So there's some intrinsic relationship between electricity and magnetism. They are related somehow. Okay? And you can see this in the fact that as kids, probably most of us at some time or another, created a very, very simple electromagnet. Okay? If you were, allowed to play with things like batteries and sharp nails. I know nowadays maybe kids aren't allowed to do that, but back in my day, parents weren't paying as much attention, or they didn't destroy our curiosity by taking away fun stuff like batteries and wires and nails and whatnots. Okay, but anyway, if you take some wire, okay, and you tightly wrap it, I'm drawing a loose wrap here, but you tightly wrap some wire around this, okay, and you could try this at night. Maybe you're old enough now to try this out. I don't know. Get yourself a 9 volt. Doesn't have to be a 9 volt actually, just any battery really, and hook this up. Okay, and what you will get is you will get a flow of charge around here, and this would be a iron or steel nail. Okay, and remember, in electricity we say current flows around like this, and what you will end up with, okay, is a piece of iron that was not a magnet before, but that now is. So while current is flowing, this paramagnetic iron nail will be able to pick up things like paper clips or other very light things, like maybe used staples and so on. Okay, and it will turn out, and we'll talk about this later, but it will turn out that one end definitely becomes the north pole of this magnet, and one end becomes the south pole. And this should demonstrate to you, and demonstrated to people, in the, say, late 1600s, when batteries got kind of good enough, that there's a definite relationship between electricity and magnetism. And I've actually also heard that if you happen to be outside with a compass, and I mean, people don't really use compasses nowadays, but for many, many years they were a very vital navigation instrument. And if you, say, happen to be at sea trying to get a bearing from your compass and lightning were to strike nearby, early navigators noticed that caused their compasses to do strange things. Okay? So the relationship between electricity and magnetism, although in the terms of human history is a fairly new idea, in terms of just modern science, it's been known for quite a while that there's some kind of relationship between those things. Okay? And it should make sense, right? Knowing that it comes from this kind of magical little particle called the electron. And technically, I think probably from protons as well, although I don't really know about that exactly. Okay? So the key here is that it is actually moving charge. Charge sitting still, just a charged object, will not exhibit necessarily magnetism, but charge flowing through wires will. So moving charge causes magnetism, okay? So I'm just going to leave that at that. We're going to go more into electromagnetism tomorrow. I just want to get back to actual steel magnets or iron magnets and just see kind of how we think about them. So what I'm going to do here is draw ourselves a magnet. That's not what I want to do. I want this. This. Okay. There we go. So the first thing you'll probably notice is that a magnet is decorated usually with an N on one end, and that is often colored to red. And blue to the other end. Okay? So what does that mean? Well, this is defined based on essentially how these guys react with compasses. All right? You know what a compass is? You remember what a compass is? So a compass, if you don't know, I think you should know, but if you don't know, imagine that you put a little rebar magnet on top of a pivot so that it can swivel around. Okay? Compasses react to Earth's magnetic field, which we'll get to in a bit. Okay? And basically, they aim their point towards north. Okay? So if I look at a compass from top down, all right, basically it's going to be like a little pointer. It's going to be red at one end, usually blue or just uncolored at the other. And it's got a pivot, and it points to the north. Okay? So you lay it on the ground, and it will point north. So if I take a compass, and I put it near a bar magnet, all right, I put it near a bar magnet, what you will find is that compass will actually do this. If I put it right here, it's going to do this. Okay? It is going to be, the north end of the compass is going to be repelled away from the magnet. We're going to do a little demonstration of this in a minute. It's going to be pointing away, right? You probably know this already, but if you don't, like poles repel. So just like kind of with charge, like charges repel, like poles repel. So if I take a north magnet and a north magnet and try to jam them together, there will be a repulsive force. If I bring the south pole of another magnet nearby, there will be an attractive force. Okay? And opposite poles attract. Notice I'm not saying charge, I'm saying poles. Now, you're going to imagine, like we did with the positive test charge, that you're moving a magnet around in space and seeing what it does. Okay? So if I take this compass, sorry, I should have said compass there. If I take this compass and I put it over here, it's going to point like that, isn't it? Right? It's going to point towards the south. It's going to react to this thing, react to this big magnet. And if I put it over here, okay, if I put it over here, it's going to kind of point that way, right? And if I put it over here, it'll still point that way. So what this is doing is it's essentially, and you can imagine me moving it around in space, it's essentially pointing the direction of the magnetic field. So this is how we define magnetic fields. We say, whichever way the compass would point, that is the way the field is going. So here, the field's going like that. If I were to move my compass over here, we'd see this, and this, and so on. And we would see that these would come in to the south. So on a larger scale, okay, if I were to take that same kind of picture that I just had, big permanent magnet, okay, oops, north end here, south end here, and I were to draw the entire field in based on what the compass is doing, I would find this kind of a thing. Okay? So very similar to the sort of shape that you get with an electric field, okay, shape-wise. It's just that there's always a north and a south pole on every magnet, and we'll get into that in a minute, okay? So the rule of thumb here is magnetic fields point out of north and into south. Okay? And the way to remember that is just, what would a compass do? Well, a compass would point away from the north and into the south. This brings up an interesting issue. If you think about the way that a compass is set up, okay, let's imagine that we have our planet here, right? Which we're navigating on with our compass. Okay? Oh, for goodness sake. Every time. So we've got the equator here, right? We've got what we call the North Pole here. We've got the South Pole here. Now I take my compass and I'm standing here. That compass is going to point like this. Okay? Well, that's weird because we just said that the North Pole of a compass points to the South Pole of a magnet. So what does that tell you about Earth's magnetic field? Well, it must tell you that it's actually like this. It's south up here, it's north down here in terms of magnetism. So direction-wise, yeah, we call this north because the North Pole of our compass points there. But magnetic field-wise, this has to be the South Pole. So if you look at Earth's magnetic field, what you're going to find is it aims like this. Right? Just like our compass is going to point. Okay? And we say things like magnetic north, but really we should be saying magnetic south. I know, crazy. What you gonna do? That's the way it is. So there can be confusion, right? Earth's north direction is actually the South Pole of Earth's magnetic field. What? Yeah, that's how that is, right? Just based on our definitions of North and South Pole and what a compass will do. Mention that. The reason Earth has a magnetic field, though it's not completely understood, the core is iron nickel. Probably has a solid nickel core with molten iron around it. Both of these are magnetic metals, magnetic properties. And being that they're molten, they move around, right? You can imagine looking into a volcano and just seeing all that lava moving around. That's kind of like what's going on deep under the crust of the Earth. And those are magnetic materials. A consequence of their movement is actually that what we call magnetic north, which is really a south pole, but we call it magnetic north, it like wanders around up here, okay? So it just moves around. So when you're looking at your compass, you have to like kind of know where magnetic north is with relation to true north. We know where true north is because there's a special star called Polaris that is exactly in line with Earth's axis. So that's where we say true north is, right? Wherever Polaris and the Earth are lined up, at least right now. I don't want to get into it, but Earth actually precesses, so it wobbles a bit. But for right now, we can just say this is true. Okay. And the last thing I want to talk about with permanent magnets is the concept of domain theory. Okay. So it's sort of a simple concept, and it just makes understanding what happens when you deal with magnets a little easier. So what we'll say is, inside all materials, you have domains, regardless of what they're made of, okay? Okay, so let's see. And, you know, just in everyday existence, these domains are oriented like completely randomly, okay? And what a domain is it's like a little magnetized area. Okay, so we're going to think about it in terms of domains. We're not going to get into the spin of electrons. We're just going to keep it simple with there's little areas inside stuff that act like little magnets. Okay? If the overall scenario is that these are randomly aligned, then basically all of their fields as a sum, the sum of all of these fields cancels out. and there is no magnetism. Okay, but you could align them. You can take this guy and you can cause his fields to align. Yeah, it doesn't want to copy and paste either. I'm not sure what's going on. Okay. I have to send this program into the shop. Okay, so let's say we have that same material, or roughly a similar material, and we'll say it was soft iron. Okay, if I bring another magnet nearby, what will happen is these domains will line themselves up. Okay, and then what will happen is the sum of all of these little magnetic, basically like little magnetic areas, will create the magnetism that you would see, right? So it will build a magnetic field. So this will become north and this will become south, all right? So where domains can be permanently lined up and stick, if they stick, we have a permanent magnet. If they just line up while another magnet's nearby, well, then you have a paramagnet. Okay, does that make sense? So if I were to cut a magnet in half, right, I'd end up with two new magnets, right, with a north and a south pole each. So there's no such thing as a magnetic monopole. Okay. Now this is probably a very, if there's actual like solid state physicists watching or quantum physicists or whatever, this is probably an extremely simplified view. And I'm not even actually sure if this is totally true. But for all intents and purposes, for everyday dealings, this is true. There's no such thing as a monopole. So I can't cut the north end of a magnet off and say separate it from the rest. Because if I cut it, right, due to domain theory, this would just have a south end at the back. Does that make sense? I'm just going to quickly blast the last thing. That's diamagnetism. We're not going to talk about this for very long. It's just that any matter exhibits some magnetism if an extreme magnetic field is applied. But